here's our next question with Bernoulli's principle. All right, we've got a dam, and the dam has an intake valve that's 50 meters below the surface of the water. So right here, that's our 50 meters. Sorry, my meters got lost there. And then the pipe takes it all the way down to the turbine over through a drop of 200 meters. And then we've got the turbine down at the bottom. It gives us the diameter of the intake, 100 centimeters right there. So 1 meter is the diameter of the intake. And then it also gives us right here through a tube before entering the turbine through a 50 centimeter diameter pipe. So down here at the bottom, 50 centimeter diameter. All right. And the question, it does say the turbine is open to the air. That's significant because that means we know what the pressure is down there. It's the same as whatever the pressure is outside. Open to the air always means pressure, atmospheric pressure there. All right, the questions are, what is the water speed at the end of the turbine? So down there, as it enters into the turbine, what's the water speed down there? And secondly, how much does the intake pressure differ from the pressure of the turbine? So those are two questions we're hoping to answer here. Now, it's often very tempting when it asks what is the water speed of the turbine to say, oh, so I need to know the speed of the turbine, so if I know the speed at the beginning, I can use the AV because the size of the pipe is changing. Problem is, we don't know the speed at the intake. So there's definitely an easier way to do this, all right? Now, when we approach this question, again, this is like conservation of energy. Our beginning and ending points are going to be the most important things because that's going to determine whether we're going to be able to answer a question or not. All right, so what I want you to do as you look at this and as you start thinking about, well, the fluid's flowing, that means it's probably going to be Bernoulli's, right? You got some velocity at the end, it's talking about pressure. It's a pretty good Bernoulli's question, right? So there are really three different places where we have things happening, okay? One is right here at the surface of the water, okay? Now, that's an important point because we know what the pressure is there. We know that the pressure there is atmospheric pressure, okay? Secondly, we know what the velocity is there. If this is a big, huge reservoir, then the velocity of the water there is essentially zero. Even if water is coming out here, it's not going to be dropping that fast. And the likelihood is you got water coming in, water going out. The level of the water is going to be close enough to zero for the velocity that we don't have to worry about it. Third of all, we know exactly how high that is from the bottom. We know how high it is from the intake. So we've got Y there, right? So we actually have all the information we need, more or less, understanding that it is atmospheric pressure, whatever that is. Okay, so that's an important point to recognize that we have. Secondly, we've got the point right as it starts going through the pipe here, right? Now that's important because right here it does say how much does the intake pressure. So the intake is right here where the water gets taken into the pipe. So how much does the pressure at the intake differ from the pressure at the turbine? Which we already said, because the turbine is open to the outside, the pressure here, whatever that atmospheric pressure is going to be the same as the pressure when we get to the turbine. All right? So we don't know the pressure here. That pressure is going to depend on depth, height, speed, right? It's going to depend on those things, all right? Now, you don't want to just use the rho GH because there's some motion there as well. You can only use that pressure equals pressure plus rho GH if the only pressure is due to depth. Because we've got some speed here, we have to use this instead. All right. Now, the last place that's important is down here at the bottom, right, where it's coming out of the pipe and into the turbine. Okay, so we're looking at the instant after it leaves the pipe. So it still has whatever speed it has there, but the pressure is going to be not what the pressure is in the pipe. The pressure is going to be atmospheric because it's open to the outside. It's open to the air. All right, so those are the 3 points we're looking at. Now, the first question is asking about what is the water speed at the turbine. All right, so I definitely need to use that last point there, but which other point am I going to use? I need a point 1 and a point 2. Well, hopefully you're noticing that I don't really know very much about this point at all. If I knew the speed there, then yeah, I could very easily use that speed to determine the speed here using a1v1 equals a2v2. I don't have that though. So instead, we're going to use Bernoulli's starting up here at the top of the dam, at the surface of the water, and then down here. Remember, with conservation of energy, whatever happened in the middle didn't matter. You could start at the top of a hill, go through a loop, go up a hill, down a hill, and then end at the bottom, and you could do conservation of energy for all of that. Same thing for Bernoulli's principle here. As long as everything is contained, we're not losing any energy or pressure there, we can go ahead and just use point 1 and point 2. All right, so point 1 at the surface of the water, the pressure is going to be atmospheric pressure. So I'm just going to label that P1 just like I did in the picture, plus 1/2 rho V squared. And remember, we talked about the fact that because the water level is not changing, then the velocity of the water there is essentially 0. So that term's going to go away. Then we've got plus rho G Y. So plus rho, which is 1,000, it's still water, we'll assume that, times G, which is 9.8, times Y, which is the height, remember. Now in this situation, since we're looking at this point down here, let's go ahead and define this as 0, which means that the water is 250 meters above. So we'll go 250 there. All right, so that's point 1. Now point 2 is going to be down at the turbine as the water starts spraying out. Again, the pressure is going to be atmospheric pressure, P1. So it's going to turn out that it doesn't matter that we don't know what it is, because it's going to end up canceling out. Okay, plus 1/2 rho V squared. Density still is 1,000. That's the velocity we're looking for. Plus rho GY, but because I defined that as 0 height, this will be 0, and that term's going away. So that's what we end up with. Now we subtract the P from both sides. Where's my red cancel marker? These guys are going to go away. Cancel, cancel. And then from there, you should be able to just beep, 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 plug it into calculator, work it out, and I got that my velocity is 70 meters per second. Ta-da! Bernoulli's principle. All right, now that's only part A. We can move on to part B here. Part B says, how much does the intake pressure differ from the pressure at the turbine? How much does it differ? What does that sound like to you? Relative pressure, right? It's asking about the relative pressure between the intake and the pressure at the turbine. So we need the relative pressure between this point and that point over there. All right, we're going to go ahead and change colors so it's not confusing. We are going to use Bernoulli's principle again. You've got a choice. You've got a choice. Because the pressure here is the same as the pressure here, you can use this point and that point. Or you can use this point and that point. Remember when we did conservation of energy, sometimes you had a choice. You could choose which ones would, and multiple ways would work. I'm going to go ahead and use this one and that one, just because I think it'll be fun. Why do I think that one will be fun? I don't know. I just chose that one. All right, so here we go. We have the pressure here, which we don't know what that is. That's what we're trying to find. So I'm going to label that as P2. Okay, plus, now I'm going to have 1/2 rho V squared. Now here, there is some velocity, right? Now I don't know what that velocity is, but now that I know this velocity, I can get it, can't I? So I'm going to have to go think outside the box a little bit. I'm going to go over here. I'm going to say, oh yeah, I need my area 1 V1 to equal area 2 V2. So we are still going to use this. We're just using it in a different time, a different place than we did before. So area 1, remember that the diameter of that was 100 centimeters. So the radius would be 0.5. So that would be pi times 0.5 squared, pi r squared, times V1, that's what I'm solving for, is equal to area 2, which would be down here because I know the velocity there. That's what I just found. And so I'll put that in. So it'll be pi. The diameter was 50 centimeters. That's 0.5 meters. So the radius is 0.25. So 0.25 squared, and then times V2. Now, you may be noticing that the radius is twice as big. If the radius is twice as big, and I'm going to square that, that would be 2 squared, so that means this right here will be 4 times bigger than that. Now, if this is 4 times bigger than that, then the velocity needs to be 4 times smaller than that, and because this velocity right here was 70, you may recognize that all you have to do is take that 70 and divide it by 4, and you get your answer. Now, if that reasoning doesn't make sense to you, don't worry about it. You can work it out. You can take this, you can divide both sides by the pi, divide both sides by the 0.5 squared, and you should then be able to get your answer of 17.5. Okay. And again, that should make sense because it's going 70 down there. Up here, it's wider, has a much wider pipe, right? It's twice as wide, which means the area is 4 times as big. Therefore, it should have less velocity there in order for the volumetric flow rate to stay the same. So we're going to go ahead and put that in now. So we've got 1/2 times the density, which was 1,000, times the velocity, which we just found, of 17.5 squared. Now we're going to add in the rho gy. So 1,000 times 9.8 times y. So the height here is 200. So we put 200 there. All right. That will be equal to everything down at our final point there at the turbine. All right. So remember the pressure here is P1 plus 1/2 times the density times V2. Density is still 1,000. And the velocity was 70. And rho gy, but the y, the height down here, that's where I define my 0. So that term's going to go away. So that's gone. And so I should now be able to calculate for the difference in the pressure. Now the difference in the pressure is going to be that P2 minus P1. All right, we do expect the pressure. It's a little hard to tell here whether the pressure should be bigger or smaller. It's deeper in the water, which that would be a higher pressure, but it's moving faster. And moving faster would actually end up being a lower pressure than what we have up there. So we expect it to, it's hard to know which one of those is going to have a larger effect. So let's go ahead and see if we can figure it out here. Go ahead, punch those numbers in. I'm going to move the P2 over to the other side. So I'm going to end up having P1 minus P2. So this is moving over there. This one needs to move over to this side. Okay, so I'm going to go ahead and punch all that in. I got negative 336,875 pascals. So what that means is that P2 is that much bigger than P1. Okay, so the pressure here is much, much, much greater than the pressure there, which makes sense because it's being pushed into and through the pipe. And so there should be a high pressure pushing down to the low pressure. All right, that's all we got. So that's it for this question. And hopefully that's enough to help get you started on working through some problems. All right, see you next time.